Welcome to the 19th lecture on digital simulation. In this video, we will discuss about stiff systems. So consider a system of ordinary differential equations of the form x dot equal to ax. So if the magnitudes of the eigenvalues of this matrix A are far separated in magnitude, if the magnitudes are significantly different from each other, then the system of ODEs is called a stiff system. So we can find out, we can see examples of stiff systems in chemical reactions involving several reactants, or motion of masses connected by springs, or in electric circuits. So we will see an example from electric circuits. So the definition is this one: if the eigenvalues of the A matrix are separated in magnitude by large values, then if one eigenvalue is very small and another eigenvalue is very large in magnitude, then that will lead to a stiff system of equations. So suppose we have an electric circuit like this, consisting of two resistances and two capacitances with zero initial conditions. We can write Kirchhoff's current law in these two nodes. Suppose I consider only these two nodes. So we at V1, at node 1, we can write V1 minus V0, this is by R1, that is this current, plus C1 into dV1 by dt, plus V1 minus V2 by R2 is equal to 0. This is a KCL at node 1. And if you rewrite, you will get this differential equation in V1. dV1 by dt equal to this RHS. Similarly, you can write KCL at a second node, and that is current going out from second node through this R2 is V2 minus V1 by R2, plus current flowing through this capacitance is C2 into dV2 by V2. This is equal to 0. So that is written here. This is a KCL at node 2, and if you rewrite it as a differential equation in standard form, you will get dV2 by dt equal to this right hand side. Okay, so for these given values of R1, R2 and C1, C2, R1 is equal to 0.5 ohm, R2 5 ohm, C1 0.01 microfarad, 0.01 farad, C2 1 farad. The eigenvalues will be far separated in magnitude. Let us evaluate the eigenvalues. So in the previous two equations, this is equation number 1 and this is equation number 2. These two equations can be written in the matrix form like this. So this will give you the A matrix. So if I plug in the values of R1, R2, C1, C2 in this matrix, I will get this 2 minus 220, 20, 0.2 minus 0.2. You can check this. And the eigenvalues of this matrix can be evaluated using MATLAB. If you compute eigenvalue of A, you use this command I of A. You have to first define the matrix in MATLAB. So let me show that. So A equal to minus 220, 20, 0.2 minus 0.2. So then you check I of A. So you can see one eigenvalue is minus 220 and second eigenvalue is minus 0.1818 or minus 0.182. Okay, so if you give the values, if you check the values of the lambda 1 and lambda 2, they are far separated. And what is the consequence of that? The general solution is of this form: x of t is equal to a into e raised to minus t by tau 1 plus b into e raised to minus t by tau 2 plus c, where tau 1 is the time constant given by 1 by lambda, magnitude of lambda 1, and tau 2 is the time constant which is given by 1 by magnitude of lambda 2. So if you evaluate tau 1 and tau 2, tau 1 is 1 by 0.182, so it is 5.5 seconds, and tau 2 is 1 by 220, that is very small, 0.0045 seconds. So the time constants are far separated. So this time constant is very large compared to this time constant. So this will be a fast transient, this will be slow, this response will be slow, corresponding to this eigenvalue lambda 1. Response corresponding to eigenvalue lambda 1 will be slow, response corresponding to the eigenvalue lambda 2 will be fast. So you can clearly see that if you solve the system using MATLAB, I will teach you how to write these equations in MATLAB and solve this in the fifth module. So for the time being, let us look at this simulation result. So if you solve the above system using forward Euler method with this step size h equal to 0.002, you will get the plot of v1 like this. So you can see initially there is a fast response. This is due to that lambda 2 0.045 seconds time constant corresponding to 220, lambda 2 equal to minus 220. Then there is a slow response corresponding to lambda 1, that is due to minus 0.1818, that lambda 2. So there is a faster response and a slow response as we expect. And if you increase the step size further, this step size is 0.002. If you increase the step size to 0.01, you can see the forward Euler method becomes unstable. Okay, there are increasing oscillations and the method is now unstable. So let us evaluate the performance using backward Euler method. If you check backward Euler method with the h equal to 0.002 or h equal to 0.01, in both cases you will get expected result. The method is stable since this is an astable method. This backward Euler method is an astable method. That is why even if you increase the step size, the method is still stable. So whereas a forward Euler method becomes unstable with the larger step size. So this is about stiff system. Now we will continue in the next video. Thank you.